I'm good. I'm sad.
Let's see, today's Wednesday, right?
Yeah, today's Wednesday.
Wednesday.
Wednesday, all day.
This is the worst thing.
All right, explain everything you see.
Yeah, that's cute. That's all that matters.
Describe everything you see.
Both have the same KVP,
Yeah.
same max energy photon.
The low-hanging fruit, yes.
Yeah.
Same target?
Same target.
Same characteristics.
Same characteristics. Same target.
Um,
Let somebody else jump in there.
Oh, sorry.
Back row. You're hiding back there in the back row. I see you. I can't see you clearly, but I can see you. Third row, you want to chime in there? You're not going to let the second row people do all the work, are you?
Yeah.
Okay, then we can go for the left and right sides.
The top one has more photons.
The top one has more photons than the
B.
other one. So do we get those four things? Same max energy, same KVP, same target. You've got the one distribution has more photons than the other. And there's one more bit of information.
Oh, the max average
The
is.
max average. Are you want the average or the
No,
max?
sorry, the average.
The average, yes. What about the average?
Different average. What different averages?
Different averages.
Average energy is
Can we
bigger for the.
enlarge upon that just slightly? Different averages.
The average energy of the photon is bigger for the taller wave, X-ray.
Lack of labels. Let's call this A and we'll call this B. Compare the average energies of A and B.
Average energy of A is bigger than B.
Why do you say that?
I think B is bigger than
The average energy of B is higher than the average energy of A.
Oh,
Yeah. Where are those averages? What are we looking at? The median, yeah, the median is a pretty good idea.
oh, that's right.
So the average energy of B is about here. The average energy of A is about there.
Oh, I forgot.
So, let's see, what do we got thus far? The average of A is approximately what? Let's call it 40, and the average of B is approximately. And then let's just remind ourselves of what the other major factors are. A has more photons than B. You have the same target and the same KVP. So what has happened to the distribution? Differences between A and B.
A has a higher mass.
A has more mass than B. Yes. Put that down here too. greater than MAS of B. So how did we go from A to B? What did we do? If we started with B and we changed something, what did we affect? What did we do?
You mean how we got from lower number of photons to higher number of photons?
Go the other way.
Okay, from higher to lower.
How did we go from a higher number of photons to a lower number of photons?
The KV got higher or lower?
The KVP didn't change. The tube setting of the voltage didn't change. The target didn't change. What did we do to this distribution? What is it, the significant difference between these two distributions?
Less photons.
Number of photons and the energy.
Is it like hardening or something?
Hmm?
Hardening or something?
Hardening.
Yes, in the book I read that.
In the book you read that,
In the
yes.
book I read it.
It's in the book, I'm sure. Okay, it is that. That is exactly what it is. She nailed it. It's filtration.
Good job, what?
We've removed the low energy photons. That's the significance of this one. Low energy photons have been removed.
I wouldn't have guessed.
You weren't supposed to guess, you were supposed to know. So what we're saying is that the low energy photons have been taken away. This is the part that's been removed. So all of those photons got absorbed in the filter. Notice that the filter doesn't really affect the high energy photons very much. The filtration strongly affects the low energy photons. Low energy photons are strongly absorbed. And what this has the effect of doing is changing the average beam energy. So how to increase the average beam energy without increasing the beam energy? Sounds like a strange idea. Just think of it as no child left behind for the X-ray beam. How do you improve performance? You get rid of the underperformers. That's all there is to it. You don't change anything, you just make the people that can't do it go away. And then your performance looks great. Anyway, sort of an old joke about no child left behind. Okay, so that's one of the little harder things conceptually in this chapter is to get used to the idea that you can change the average without changing the maximum. And you're changing the average by removing the low energy photons. And so now your average beam energy is larger, and your beam is more penetrating now. Or it's also expressed as a harder beam. And so to put that in the words that we're using, we would also describe it as B is harder than A. Why is B harder? Because it has a higher average energy. Does not have a higher maximum energy. Let's be really clear on that point.
We're saying that B is harder than A,
Yes.
although I thought we got. I'm confused with the wording and the graph now.
Yep.
So
B
A
is
has,
harder than A, that's right.
so although A has no more number of photons, but the quality is not all of them are good, so B has a better quality, which is the,
B is better quality, yep. So B has a higher average energy, but B does not have a higher max energy. So you have to separate those two ideas of maximum and average. And remember which one you're talking about. Any leftover questions about the shape of these two graphs? You haven't figured it out yet. That's a tough one. That was a tough one. Let's try another one. Same idea. What's going on?
Same characteristics.
We've got 4 things to work with. 5 things. What things? MAS, KVP, target characteristics, average energy.
All three have the same KBP.
and same target.
Same target,
Oh, so
same
you
max
pick-
energy,
Same KVP, same max energy. That's the same thing.
but
Same target.
differing average.
Differing averages. Yes.
Same binding energy.
Same binding energy. How are you getting to that?
The characteristics.
The characteristics. Yes. Meaning the same target.
Good job.
You're equating that spike out there with the K-shell binding energy, yes?
Yes.
You would say, what is the K-shell binding energy for this target?
What's the question?
What is the K-shell binding energy for this target?
70.
70.
Or
I say 70.
Yeah, 70,
68,
69, yeah.
70.
Can't really, since it's not really labeled very well. K-shell binding energy is about 70. What is the significance here?
Do we say that A has the harder,
Where are the averages?
C has the highest average.
C has a higher average. A has the lowest average. B is in between. Okay. So smaller MAS is associated with A, less photons. So A has less photons and lower average energy. B has more photons and a higher average energy, and C has more photons still and a slightly higher average energy. Same target, same KVP. Is it time? Is it time for what? Well, if you change the time, then everything would be the same, except for the MAS. The MAS is affected by time. But it seems like the average energy is changing as well. So we want something that produces lots of low energy photons, and then we want to improve it by having less low energy and more mid energy photons. And something finally improves it even better with even less low energy photons.
Filter.
Filtering. That was in the previous graph. Notice how these two graphs, notice where the peaks are in these two graphs and the way the averages go. Got that memorized? Then we go back here. Just what is the difference in the organization of those peaks? Right, the lower one has the higher energy, and in this next one, the lowest one has the lowest energy. Interesting. So we're increasing, as we go up, we're increasing the number of high energy photons. We're not getting rid of, well, we're increasing the number of high energy photons by doing something. And it's not filtering.
By increasing the KEV.
They have the same maximum KVP. They have the same target.
By increasing the voltage.
We have not increased the voltage. The voltage is the same. The target is the same.
Little vertical lines.
What else can we change?
I think it's the same thing.
This one is another kind of obscure one. Voltage waveform. You're seeing ripple. How is this graph describing ripple?
So C would be like the high frequency one?
C would be like the high frequency or least ripple. What is the difference between A and B?
The number of photons produced.
In terms of waveforms, might you speculate?
That maybe the ripples are bigger in A than in B.
Okay, that's a fair way to say it. What is that waveform? Name that
This is the
waveform.
three
A
phase.
single phase,
Single phase.
and then these three phase.
Okay, can you tell me a little bit more? You can tell me a little bit more. You can tell me whether it's half wave or full wave rectified. You might speculate.
Yeah.
Now let's say that A is full wave, but single phase. And let's say B is full wave and three phase.
So they're both full waves.
They're both full wave.
Oh, okay.
Fair enough. What is the ripple for A?
100%.
100%. What's the approximate ripple for B, assuming it's three phase 6 pulse or whatever they tell me?
12%.
About 12 to 14%, something like that. And then if C is high frequency, what's its ripple?
Less than 1.
About 1% or something less than that.
Yeah.
Yeah. So what does more ripple do for you?
Less high energy photons.
Less high energy photons. Everything that's bad happens in that graph with ripple. So that's what you want to think about. You're thinking, this demonstrates ripple very clearly and why it's bad. More ripple, more low energy, or you're getting just, it's less efficient and you're producing more low energy photons, or your average energy photon is lower is what I mean to say. So, do we got all those four things?
I have a silly question.
Go for it.
How did you figure out all these? Are we assuming or analyzing, or it's just from the picture we got the hint that it's high frequency?
We don't really know. We just know that there is probably a little bit of difference. And the only thing that it could depend on, given the way that the averages are going there, same peak, same target.
How do you know it's a single or three phase?
Oh, you can't see. So you can't see the
Oh.
single or three phase.
So we assume according to the difference in the average.
Let's take a look at what does single phase look like. This is voltage. This is time. Single phase, full wave rectified. We're looking at that. And then three three-phase. How does three-phase differ from single-phase?
You have
It goes to.
multiple waves
No more
Multiple
than-
waves,
And
yes.
it goes down to
at
no more
different
than
times to
14%.
prevent the voltage from dropping to very low.
So we're thinking of three-phase that looks something like this. And presumably this is looking at that, and this one is looking at that. And the fact that you get this low energy region and very little time spent at the top is why this peak is shifted all the way down there. Yes? So the filtering and the waveform are probably the two challenging graphs in that whole section.
So figure it out by comparing the three waves to each other.
Three waves to each
Yeah,
other.
A, B, and C.
Yes, you're looking at relative differences. Let's say that this is high frequency. Let's say that this is three-phase. Full wave. This is single phase. And what's being demonstrated here is the voltage waveform dependence of the X-ray spectra. Leftover questions? Well, that and this. Here, let's see, it should be here. Okay, here, you just draw a graph demonstrating the MAS dependence of the X-ray spectra. Without looking at your notes, eh? What is the MAS dependence of the X-ray spectra? Let's see. MAS relates to what? Pardon?
The number of photons.
The number of photons. It's related to the number of photons. MAS really refers to what?
Time.
Milliamp seconds. And what are we talking about in milliamps? What is milliamps? What are we measuring in milliamps?
The tube current.
Tube current. And current times time is What?
Charge.
Number of electrons. What we're really talking about is the number of electrons hitting the target, but that is somehow related to the number of photons produced. We don't know how, but we assume it's in a nice way. So, if we're just changing the number of electrons hitting the target, what are we not changing? I think we're not changing the KVP, or the energy of these electrons. We're not changing the target. So what does this, what graph would demonstrate this MAS dependence? If you haven't changed the maximum energy, you haven't changed the target, so you haven't changed the characteristics, and you haven't changed the average energy. What do those two look like?
The same, but one's just taller.
The same, but different, yes. Whatever you draw one, and you draw another one that's bigger, having the same average and the same peaks and the same basic shape as best you can. And of course, you should indicate that they should have the same target and the same averages. And then, of course, it would be nice to add a label, something like A and B, and make a statement. Was that a surprise? Not really.
And then the number, is that number of electrons or is that?
Number of photons.
Photons.
Okay, your next challenge. Draw a graph demonstrating the KVP dependence of the X-ray spectra and the 15% rule. What is A? What is B?
Just moving short. Like you're given the x-axis starting 100, it's all like 85.
You could do it that way. I mean, I didn't specify how to do it, but I was thinking that B would have a something that would demonstrate an increase of KVP by 15%.
maybe B would have if it's the bigger one, it would have a higher max KVP.
Well, okay, let's say that B has a higher max KVP. How much higher?
50% more.
Where is 15% on that?
Like some space to the right of
Some
the
space to the right, yes.
right of the max KVP of A.
Okay,
Yeah, right about there.
all right. So there's our B. What else?
And
MAS is going to double when we increase the KVP by that much. Now, what does it mean to have the MAS double?
the lower KVP.
Well, MAS is area, so you want to make a second curve that has twice the area of A.
More number.
Peak double or with the average?
Good question. The peak double or the average? Does increasing the KVP change the average energy? See, all these little things you have to keep in mind. If you increase the KVP, do you increase the average energy? Higher maximum, yes, you're also going to increase the average energy. So the average changes as well. So if here's our average energy for A, let's say that the B average energy is maybe here. So now you got to make a distribution that has basically twice the area and has that as its average. Something like that would kind of do it. So the high points are, B has twice the area. And we're thinking that is related to MAS. B has higher average energy. Max energy. And we would like to, because we always remember that we like to see that target dependence. B has the same target. Any surprises in all of that? Yeah,
Which homework is this?
I don't know. It's the homework that you're gonna do before the next test, right? Whatever it is.
Hopefully I haven't seen it.
I don't know that it's there,
Um,
but you'll practice this chapter, looking at these graphs. So what have we done so far? We've drawn a graph demonstrating the MAS dependence. You've drawn a graph demonstrating the KVP dependence. Draw a graph demonstrating target dependence. Doesn't have to be quite as detailed as the one sample in the book, but it's a good one to have in mind. Something that illustrates the key features of large targets, heavy targets, and light targets. comes to mind immediately is the characteristics.
Yes.
So they're gonna have different characteristics. And heavier targets produce more high energy photons. Light targets produce mainly low energy photons. So they're gonna have different averages.
You're talking about the composition of the target? How the
Yes.
metals made up? Okay.
Yes. For example, something like copper versus gold. Copper's about, well, gold is 79 and copper is 29, whatever, about a third of it. But you should be able to get these, illustrate these differences. The heavier target has higher average energy, more high energy photons. The characteristics change. The maximum energy of the photon. Does that change just by changing the target? What does the maximum photon energy depend upon?
KVP.
KVP. We're not changing the KVP,
So no.
so they better have the same max energy photon. Put our maximum out there. And our low or small or lightweight target does something like that. And it's got maybe a peak down there. And our high energy target, our heavy target rather, does something like that. And maybe it's got some peaks there. This being the K shell. In the different cases, and of course you notice the average. So we'll call that A, we'll call that B. B, the average beam energy there. That's not too hard. Once you practice that one, that's much easier than, say, the filtration or the voltage dependence. Yes,
It looks like he has more mass than A.
it does. The heavier target also produces more photons.
So there's 5 graphs.
Wait.
There's 5 graphs, yes. I was waiting for someone to figure that one out. We've done 3, what are the next 2? Can you do them without looking at your notes? Demonstrate filtering. So, without looking at your notes, let's see if you can remember the key features of filtering. Make that graph that demonstrates no child left behind. We get rid of the low energy stuff, the underperformers, we make them disappear. So we're increasing the mass, we're increasing the average, we're decreasing the MAS, keeping the target and the KVP the same. So in the lingo that you tend to use, and this one is always a little challenge, you tend to trip over it. Quality versus quantity. Quality versus quantity. How is that statement related to these two lines here? Going from A to B. A to B. Quality.
B has more quality than A.
B has a higher quality than A. Quality increased. What about quantity?
A has more quantity.
A has more quantity, B has more quality. Yeah, those, he uses those kind of terms here. Leftover questions on this one? Okay, that last one that you have to do is voltage waveform dependence. Here's where you're remembering that the more ripple produces fewer high energy photons. More ripple, fewer high energy photons. Less ripple, more low energy photons. So I'm going to let this be lots of ripple. I'll call A 100% ripple. And we'll let B be 14% ripple. So how does B look relative to A? More higher energy photons, yes. And we were careful to acknowledge that the targets did not change, that the max energy didn't change. But the big significance is that the average energy changed. There. So you got 5 graphs to deal with, filling in all those details. Any leftover questions on these 5 graphs? Because we're moving into chapter 8. Yeah. Just let you digest this for a second here. A little practice, and this is not bad. Oops. Oh, just summarize it. What are the factors that affect the spectra? This is a good little exercise. Okay, next we're going to move into chapter 8, which is factors that affect X-ray production. affect X-ray emission? Kind of a strange title for this chapter. What he's really thinking about is factors that affect intensity.
Factors that affect X-ray emission or effect X-ray emission?
Affect or effect, you tell me.
Let's say affect.
Factors that affect. I think it's the effect is wrong, right? I always forget. I never remember. Just write it sloppily enough and the A looks like an E. And it's don't have to admit anything.
That always works.
Yes.
That's a great metric.
So we're looking for thinking. Just what I'm trying to indicate here is that you're thinking about intensity. So now we're not worried about the spectra as much as the intensity of the radiation that the patient might experience. And so the things that affect intensity, the first thing that might affect intensity that jumps to your mind is
Distance.
distance, yes. So we're thinking about their distance, and we're imagining that we're dealing with, of course, a point source. And what is that distance relationship for a point source?
Okay. That the further you are from the source, the less intensity of the source is.
The intensity decreases as you increase your distance. What's the famous name of this law?
Inverse proportional.
Inverse square law. And how do you want to write the inverse square law for intensities?
I1 over I2 equals D2 squared over D1 squared.
Yep, I1 over I2 is equal to D2 squared over D1 squared, or some variation of that. So intensity falls off as the square of the distance. And it's exactly the same as we did the last time we saw it, so we don't need to spend a lot of time there. Okay, we have another thing which affects the intensity, which is MAS. So, MAS meaning number of photons produced. More photons, more intensity. So we're looking for something that's directly proportional. How would you express direct proportionality? I1.
I went
One over I2. There we go. So increasing the KVP increases the intensity, but it's not directly proportional. It goes as the square. We're going to play around with those, but we've got one more factor that will affect the intensity. And how does filtration reduce the intensity of the beam?
It's less photons.
There's just less photons. Yeah. So there's no formula for the filtration part of this. So our chief formulas have to do with these factors. So you have this one in mind for our KVP dependence. You got this one for the MAS dependence. And you have this one for the distance dependence. And we'll do a simple example. All right, so our simple question is, we have a starting procedure, 10 MAS, 30 centimeters distance, 60 kVp. What happens if we change the intensity to 100 kVp? What happened to the intensity of the radiation? So when you're looking at these problems, your first step is to identify what changed. So you make a statement, only the kVp changed. So you're going to say that I2 over I1 equal to KVP2 squared over KVP1 squared. And we're going to say 100 KVP squared over 60. Then we're going to calculate away. And we get 2.78. And now you have to put this into a sentence.
With more KVP, 2.7 times as much intensity.
Yeah, that works. The second process has 2.78 times the intensity of the first process. questions on what we did? Pierre?
So the 2.78 is just basically we just divide the two KDPs to get our intensity times that whatever amount.
We divide the square of the KDPs, yes?
Okay, so we don't add like the first intensity and then solve the for intensity 2. We just simply solve for the ratio for the change.
Oh, well, you could solve for intensity 2. If you did the algebra, you would find out that I2 was equal to 2.78 I1, which expresses exactly the same thing.
Oh, okay.
Yeah,
So what are the units to 2.78?
there aren't any.
Because they canceled out, right?
They canceled out. Yes, thank you for asking. As long as you have the two energies, the two voltages rather in the same units, you don't have to worry about the units. Get a little more specific here. So I got two processes. A is 15 MAS at 60 kVp at 30 centimeters. B is 20 MAS at 50 kVp at 30 centimeters. Step 0, identify what changed. MAS and kVp both changed. But I didn't give you a formula for that, so now you have to guess what to do. And that's right, you just daisy chain them together. I over IA is going to be KVP squared, A squared, MAS, B squared over MAS, A squared. And we get 0.926.
You're not squaring, or you're squaring that.
Oh, the MAS are not supposed to be squared.
It's not good.
No. We all agree on the number. Okay, after the number comes the sentence. The interpretation. Write down some verbal expression of what you just calculated.
That the intensity of B is 0.926 times the intensity of A.
Fair enough. Anyone need him to repeat that?
Can you write it down?
Repeat it one more time. You can write it down just as well as I can.
Okay, the intensity of B is 0.926 times the intensity of A.
I'm going to change them up just a little bit. The intensity of B is 92.6% that of A. So we increased our KVP, no, we decreased our KVP and increased our increased the MAS but decreased the KVP, and yet the intensity decreased. All right, one more where we change the distance as well. See if you can work out this one. I'm going to be interested in the ratio IA to IB this time, changing it up on you, keeping you on your toes. What changed? Step 0. Everything, yes. We're just going to daisy chain all those formulas together. And be careful of the distance one because the distance one is inverse. .06. We agree on the number. All
We
right.
changed the distance to meters.
Yeah,
But if we leave it in centimeters.
if you leave it in centimeters, it's fine. What about the KBB?
Oh, I said still got the
Oh, you still got the same, yeah, no, the units go away, it doesn't really matter, it didn't have to change it, I just kind of change it to meters out of a,
Easier for.
force a habit more than anything else.
When you square.
What's the sentence?
Uh,
No, not you, somebody else.
Let us think.
No, I do.
You're too fast.
Intensity A is 3.06 times the intensity B. And yeah, how do we express this in percentage?
306%.
Yeah, getting used to those strange ways that these phrases come up. One more strange one for you. Yay! Somebody's happy. All right, process A. 55 MAS at 30 centimeters. Process B. Unknown at 45 centimeters. That's why I said it's going to be strange. Then you get another little sentence to go with this. The intensity of A is the same as that of B. So your goal, figure out what intensity for B, what MAS for B would have the same intensity as A. Another way of asking the question. There's a couple of ways to think about this. But the easiest one is to do exactly what you've been doing before. Which would be something like IA over IB. But we want this to be 1 this time because they're going to be the same. This is going to be MAS A divided by MASB times DB squared over DA squared. And we're looking for MASB. So this is what we're trying to solve for. So we're going to rearrange things and say MASB equal to MASA times DB squared over DA squared. What did I start off with? 25. calculate away. And we get 56.25.
Oh, so we don't have to convert centimeters to meters?
Don't have to.
Okay.
All right, so in the textbook, and you should be very careful to make note of this. He calls it the square law, and it's on page 139. So he gives you a whole different formula to do the same thing, plus he gives you something which has a cutely named but different than the other one that's more important. So just don't trip over the square law. Bear in mind that that's just kind of put out there like, you know, something to just make you trip over it. So be very careful about that one. And all right, Monday, oh, the next test. When should we have the next test? Monday? No.
What is it? Is it up to chapter 8 or what is the next?
We're just starting chapter 8, so if we did it Monday, I wouldn't include chapter 8.
I hope I'm not doing it Monday.
I hope we're not doing it Monday. On the schedule, it says Monday. How about Wednesday?
When are we gonna get a practice exam?
Oh, that too.
Right.
Okay. Okay. So Monday's out, Wednesday is, nobody's really raving for Wednesday, I'm getting the feeling. Then what about the following week, which happens to be Thanksgiving week? Wednesday of Thanksgiving week?
Yeah.
There's no class. So we can't do it that way.
Monday?
So the Monday of Thanksgiving week, I'm happy with that. Okay, Monday of Thanksgiving week.
Yeah.
It's like the 24th, I think.
Do we have Wednesday?
Bless you.
Wednesday before
So we have
Thanksgiving is,
Wednesday, Thursday, Friday?
yes, you have the whole thing.
Oh, I didn't know that. I thought it was just Thursday and Friday. What?
Oh, you have the Wednesday before Thanksgiving, there's no class.
Thursday, Friday, Saturday, Sunday. What?
So November 23rd is the day that we're gonna do the test.
November 23rd.
Guys kidding me. My daughter, I have a question.
No.
It's fine, I'll just get everything done by.
What is it, Monday the Yeah, just have the deadline. I know that's more stuff.
You have a question about what I did?
I don't like.
Yeah. I didn't know.
Are we gonna get a practice again?
Yeah, over here. So we're Thanksgiving Day for this.
It says there's holidays.
So far,
Yes.
like if we had it Monday, it would be just on the 5 drops.
Practice test, like sometime in the future.
Sure.
Not, we just
Yeah.
did today.
Okay, practice
Quick
test.
question.
Really appreciate it.
So when would you convert to centimeters or when would you leave it?
As long as they show up in the ratio, you don't have to convert.
Yeah, nice. Seriously, this is so much writing. Yeah.
Yeah, the holiday on Monday.
That's different than what